Hi everyone, welcome to Linear Model with me, Sarini Abdullah. For this session, we will learn about residual analysis, and for the residual analysis, we will start with the motivation, why we need to do residual analysis once we have a linear regression model. So, start with, okay, when we do data analysis, of course, we want to do it because we want to, answer some kind of problems from a statistical point of view, right? So then to answer that problem, usually we need data. And so therefore, based on what the problem is, we look at the population in which we can assess that problem, and then we take sample from that population. Okay, and then based on the sample, we do some measurement. And then once we get our data, then we do our, analysis on that data using certain model. And then because we are learning about linear model, so of course we will be working with the linear model. So then once we have our data, we do our model fitting. And usually the one that we have in this lecture is using the ordinary least squares method. And then once we have our regression line, I mean that from this data, okay, we have some measurement like Y, and then we have our predictors X1, X2, and so on up to XP. And then here we propose the model that is expected Y equals beta naught plus blah, 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 plus beta P XP. And then from the result of the ordinary least squares, we have like the regression equation that is beta naught cape plus beta 1 cape x1 plus blah 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 plus beta p cape xp. And then we want to tell our story about the problem that exists in here based on our regression result. But before we tell that story, we need to make sure that this model is really useful. And how to know that the model is useful? Of course, that this thing that we call the predictors or the explanatory of Y really can explain why. And then to establish that these predictors are really good, then we have to test our model. That's why we continue with the next step, is that testing the model, goodness of fit assessment. And usually in here, we have F test. Okay, now we've done that, and then so we will be able to answer the question whether the model is really good or not. And in the case that the model is not good enough, then we have to reconsider our process in model fitting. Probably that the predictors that we are including in the model is not the ones that having like high correlation with the response variable, or probably they are strongly associated with the response variable, but no, no proper functional form that are included in the model. For example, probably we need to do some kind of transformations in the variables. You know, that kind of things we really need to consider when we refit our model in the case that the result is not good when we do the goodness of fit assessment. But if the result is good, then we can move on with the, okay, we can use X, X1, X2 up to XP to predict Y, but then how good is their performance? Then we can measure it by using the coefficient of determination, that is R squared in here, or we can also use the adjusted R squared, we can use the mean squared error, and then also we can assess which one actually from these predictors X1, X2 all the way to the XP, are they all significant or just some of them that are significant? Which one exactly that really contributing in predicting Y? Then we can do also assessment based on partial t-test. And based on this process, again, we should ask ourselves whether the result is adequate. Are we happy enough with the performance of the model? And then if we are not happy, for example, that, okay, at least one of the predictors is significant in explaining why, but then the significancy that itself is not enough. Let's say based on the R squared, it only explains about like 20% or 30% of the variability of the Y. In that case, that's kind of like low. I mean that it doesn't mean that the predictor is not good. We can say that there is a situation where that the condition exists, that is the predictor is good enough, but then it needs the inclusion of all other important explanatory in the model to increase the accuracy of the model represented by the R squared. So if we are not happy with the model's adequacy, we can just again redo the model fitting by considering including some other more important variables in the model, for example, like that. But if we are happy with the model's performance, then usually what we do is that we do interpretation of the result, and then we use the model for prediction and estimation. And the question is that, okay, everything is good. Okay, are we done with the regression? It can be yes, it can be no. I mean that if we are aware that all these metrics, like the F test, the R squared, R adjusted, mean squared error, partial t-test, they are all our global metrics. Global metrics means like, measuring the performance on average. So on average means that, okay, there might be possible that on the average it seems like everything is okay, but then if you look at each data point one by one, there might be some or a little bit or some part of the data that the performance is kind of like what is it, deviating from what we expect they should behave. So in that case, then we have to check the overall validity of the model, not just on average, but we want for each data point should behave as it is expected in the model. And what is that our expectation? That is represented by what we have when we do the model fitting in here. That is, in the modeling, that we have the assumption that the error term is following a normal distribution with independent identically distributed with the mean of 0 and the variance of sigma square. It means that to make sure that the validity of the model is guaranteed, then we have to do the model diagnostics, that is checking the model's assumption. And in this expression, we can see that the assumption on the model relies on the error term, because all the assumption here is the error is normally distributed, the error is independent, the error mean is 0, the error variance is sigma square. In that case, then we have to work with the errors. So now let's have a look at the errors. Okay, so let's say here we have our population data. Here we have our population data, and then we have this is our expected y equals beta naught plus blah 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 plus beta pxp. That is our regression line in the sense that we have or we feed it to the population data. And then let's take one point in here, and then so the value on this line is the value given by the model, and the value here is the actual value of the yi. While in here, let's say we fit the model using just a small portion or a part subset of the population data. Here we use the sample. So the line might be different from the population line. And then here, by using the same point here, we have, okay, this is the predicted value given by the prediction line, and this is the actual value. So the distance here is given by EI, that is the residual. The same thing if we take different points. So before we see that our assumption, the assumption of the model relies on the error, then we can see the error here is given by yi minus this one, and this one is estimated from the population data, which usually we don't have the population data, which means that practically we never can calculate the errors. While in here, for this line, because it's from the sample, and usually we can have the sample data, which means that we can calculate the residual. So in this case, we can say that the residual is kind of like approximating the value for the error. So then, instead of later on, when we do diagnostic checking on the model, instead of working on the errors, we will be working on the residuals. So, to sum up, we can say that residual analysis is required in model diagnostics to ensure that the validity of the model, that is, assumptions of the model, is satisfied.